All right. So fire behaviors, chapter 5. So obviously one of our first learning objectives is we're just going to explain the science of a fire as it relates to energy, forms of ignition, and modes of combustion. So we need to understand the physical science of a fire, just for our safety alone. I can move this over here. I'm gonna keep looking at it. So fire comes in a variety of different forms. Basically, it's a heat-producing chemical. So anytime we have a chemical reaction, it creates heat. And it's got to be between a fuel and an oxidizer. And what is our primary oxidizer that we can count on? What do we always, oxygen? Oxygen. Okay. So most commonly it's just oxygen in the air. You know, you're going to have other forms of it too, but that's the best way to explain it. So the knowledge we're going to gain out of this is we just need to be able to translate it into a practical fire, into understanding the fire's behavior, what the fire is going to do with what it's got available to it, and how it's going to progress based on a lot of different factors, anything from quantities to space and everything else. And then doing that and being able to recognize it, we're then going to be able to predict possibly what it's going to do based on what we know just on a quick. So here's the two types of energies we need to know about. Somebody tell me what potential energy is.
The potential of something to, it's the energy that's stored in something.
It's the stored energy that can turn into what we now consider kinetic energy. So potential energy basically represents the amount of kinetic energy that an object has. Okay? I always learned it in high school. Potential energy is as if you put a ball on the edge of a table. It's got the potential, and then the kinetic energy is when it gets pushed, what will happen to it at that point in time. Okay? So here's our different types of energies that we have. We have chemical, we have thermal, which is a lot of what we deal with, mechanical, electrical, light, nuclear, and sound. Basically, the way to look at it is it's chemical energy. Chemical energy is going to, as the process happens, turns into thermal energy. Okay? That's when you have a chemical reaction because of the friction. That's what creates heat. That gives you your thermal energy. So in your fire behavior, your potential energy, your potential chemical energy, converted to thermal, is released as heat. Okay? Measurements. We measure heat in two different forms. One way we measure is what we call joules. Okay, that's in the International System of Units, or the SI. 4.2 joules is basically the quantity is required for a change in temperature of 1 gram of water. So it takes 4 joules of energy to turn one water, or to increase water 1 degree. Okay? We're used to the BTUs, or the British thermal unit. That's what we talk about when we're talking like when we're doing furnaces and stuff like that, how many BTUs it's going to need to heat a room. Basically, that's the amount of temperature rise it's going to take for 1 pound of water to increase 1 degree Fahrenheit. Okay? So chemical physical changes involve exchange of energy. So that potential energy is released during combustion, or the burning, and that's what's converted into kinetic energy. So you take that tree that's just sitting there, it's got all that potential energy, and then the kinetic energy, or joules, or BTUs, that's what's released during the combustion, and that's where we get our converted into our kinetic energy. So here's the two different types. Somebody tell me the difference between what exothermic energy is. How do we define exothermic energy?
Exo means out.
Out, yep.
Out is the heat comes out.
Yep, it emits. It gives it off. Okay? Fireplace at home. We're sitting there at the fireplace at home, we sit around it, that heat given off is exothermic. Okay? So what's endothermic?
It's going into something else that's being used up.
Yeah, it absorbs it.
Yeah.
Okay? Endothermic is bringing it in, endo. Exothermic is it's giving it out. Okay, so endothermic, the energy that's basically converting water into steam. Okay? That's why water is our main factor, or main point that we use to put a fire out. Okay, because it takes all the heat that's being given off on the exothermic side, and it's now turning it into endothermic to use it to turn that water into steam. So, process of ignition's got to follow a sequence of steps. Okay, it's got to heat the fuel, so the temperature has to increase. Okay, so transferring that sufficient amount of heat is what we call pyrolysis in solid fuels, and vaporization in your liquid fuels. It's got to get to a gaseous state in order for combustion to occur, and we'll get into that more when we start talking about the triangle and the chemical reaction itself. But that's what's got to happen. It's got to heat it up to a certain point, so it may start as a solid, and as that solid starts to heat up, it's going through pyrolysis till it goes into possibly a liquid state, goes into vaporization, which gets us into our gases, and that's what is ignitable. Through that, we're going to go into the necessary energy provided by some type of possible external source. Okay, so what would be an external source?
Something that's already on fire.
Something's already on fire, okay? Or fuels that can heat till they're ignited, okay? And then it's going to continue through the production. We're going to get ignition, so combustion and the reaction is sustained, okay? Just because you've got a little bit of a spark, it may do something, it may not, but it's got to have enough heat still being created to continue the process, okay? Questions so far? So here's the two. Piloted ignition, simply just a match into some paper, or what we call auto ignition, which we'll get into a little bit as well, where something can just start itself. It doesn't need a heat source, it creates its own heat source. They both require similar conditions. Okay, combustion, it's a chemical reaction, can occur without a fire. Okay, so that's your flaming combustion or your non-flaming combustion. Flaming combustion, so obviously we most consider it, commonly refer to it as a fire because it has a visible flame. Pretty self-explanatory. Non-flaming combustion, as in the charcoal, it doesn't have a flame, but it's still giving off the heat. And it talks a little bit more about that here. So there's the several materials, okay? Obviously we talked about fuel. We've talked about heat. We've talked about the oxygen. And passive agents. What am I talking about in passive agents?
Absorb heat but do not participate actively in the
Right.
combustion process.
Exactly. So what items will we be talking about? In this room, do we have passive agents in this room right here? What are they? Sheetrock. Okay. Sheetrock has moisture in it, so it takes the energy that it would take to burn it is actually using to eliminate that moisture out of that wall first. Okay. Vegetation, green vegetation. You guys ever burned a ditch? All the dead stuff disappears, but what stays? All the green. It's a passive agent. It takes too long for it to burn. By the time it does, the heat's been eliminated, it stays green. Okay? On the other hand, we're using it the same way because now we're taking and looking at it in the vegetation state, and all that dead stuff is a threat to us because it is already to a point it burns very quickly. That's why when if you guys have ever been out in grass fires and field fires, what's the rule of thumb? Stay in the black. Okay? Because if you're in the green, it's coming your way and you don't know how much dead material is underneath of it. So, the two types of combustions we kind of discussed a little bit, but we're going to get into it going under different circumstances here. Non-flaming combustion occurs when the burning is localized or it's near the fuel's surface where it's in contact with oxygen. So smoldering, burning charcoal, smoldering wood or fabrics. That's what we're talking about when we're talking about non-flaming. It's in contact with the oxygen, it's just kind of smoldering. Best idea we've got, the best example we have is charcoal. It's burning, it's giving off heat, but there's no visible flame to it. Okay. Your flaming combustion, that's where your fuel mixes with the oxygen. It's the correct ratio, so we get that chemical reaction we need. Heated to its ignition temperatures. The combustion requires it's a solid fuel, it's to be vaporized, or it's got to be converted into that gaseous state. Like I said earlier, we're not going to burn necessarily a solid doesn't burn. A liquid doesn't burn. We all know that gasoline itself in liquid form doesn't burn. It's the gas that it gives off. If you actually look at a lighter, if you light a lighter, you can see the gap in the middle. It's liquid inside, but it's not burning that liquid necessarily. It's burning the gas that it's given off. Products of combustion that generate as fuel burns and changes in its chemical composition. So thermal energy. What is thermal energy? Heat. Okay. So somebody explain to me what products of combustion means. What's it described as? It's described as heat, but how else can we describe
Things that
it?
are given off from like that reaction.
The energy. Energy is released. It's given off thermal energy. Okay? So like we said, thermal energy is heat. Okay? So thermal energy, toxic smoke. What kind of toxic smokes do we have? What are we dealing with? When we get into the idea of a fire, whether it's a house fire, a car fire, what examples of toxic smoke do we have? Carbon monoxide,
Hydrogen cyanide,
cyanide,
formaldehyde.
formaldehyde's in there. Okay, so carbon monoxide we know of. What is carbon monoxide? How do we get carbon monoxide? Define it. It's flammable, right? Okay. But it's created how? Why?
By burning.
By
the
burning.
chemical reaction.
But
Uses the oxygen and
Right.
takes it.
the biggest key about carbon monoxide is it comes from the incomplete burning of something. Okay, it's flammable, but it's the incomplete burning of an organic material. Okay, that's carbon monoxide. What's hydrogen cyanide? Same thing, it's flammable, and it's produced with combustion when a certain gas is involved. Which one?
Nitrogen.
Nitrogen. Why is hydrogen cyanide so bad?
Chemical asphyxiant.
Yeah. That's the bad one. Out of all of them, that's the bad one. Okay? Carbon monoxide we know is bad. We've always known it's bad. Hydrogen cyanide is one of those that's kind of shown up that we didn't really know was there, that we're now finding. And yeah, it's a chemical asphyxiant. It gets into the lungs and starts to suppress everything, and that's what will cause you to go to having issues of asphyxiation or difficulties breathing. If, obviously, as rescue fire departments, you don't have it, there is actually a antidote for it called a Sino kit. It does exist. The hospital here has one or two of them. It's never been used. In fact, when I was teaching one time, I called up and asked about it, and the paramedic on duty says, I don't even know where it's at. Okay, so what's another gas that's given off? Carbon monoxide, it's a flammable, incomplete combustion, hydrogen cyanide, flammable, caused when you burn nitrogen. What's another one we have out there?
Particulates.
Particulates for the gas.
Sulfur dioxide.
Sulfur dioxide, but carbon dioxide. Okay. That one is a complete combustion. It's non-flammable. It occurs when you have complete combustion of an organic material. Why are not necessarily carbon dioxide? Because your body gives carbon dioxide off anyway through the breathing process, right? We already know that. Why is carbon monoxide and hydrogen, especially carbon monoxide, why is it so dangerous to us in the fire industry? We know why hydrogen cyanide is because it's an asphyxiant. Okay, it's gonna inhibit the breathing process. Well, why is carbon monoxide so dangerous to us in the fire industry?
Because our body absorbs it and can't get rid of it,
Yeah.
it can't use it.
What was yours?
Well, you can't tell it's there.
Right, you can't see it. So you can't see it, you can't smell it. The scientific version of it is carbon monoxide has a greater affinity to red blood cells than oxygen does. So it actually gets and sits onto the red blood cells. It gets in the way of oxygen, it holds on, it's there longer, and we can't tell. Well, rescue personnel can show up and you cannot be feeling right, and they start taking your blood pressure and everything else, and they put on this neat little thing called a saturation monitor, and they put it on your finger, and they say, well, you're sat at 99%. You should be fine. Why is that not necessarily correct?
It's saturated with carbon dioxide.
That saturation meter actually only reads a gas that is adhered to the blood cells. It doesn't tell you which gas it is. So, what do we see? What as fire department members can we see about somebody that we may think has a carbon monoxide issue, may have had too much in their system? What are we gonna see out of them that could tell us that maybe something's wrong? Drowsy,
Nauseous.
fatigued, nauseous. Late signs would be flush in the face, red. Okay, a little difficult when we're dealing with a fire because we're already hot, we're sweaty, everything else, so. The biggest way to avoid a lot of this is how? SCBA win. All the time. I am as guilty as the next guy. I raise my hand every time we talk about it. We go in, we put the fire out, we come back outside, the fire's been contained. Now it's time to do what? Overhaul. What do we do when we go into overhaul? I still got my pack on, but where's my mask?
It's angled down here.
Okay. The building's been on fire. It's still smoky in there. We still have all these factors that still exist. Okay. SCBA's all the time. No matter if you're a rookie or if the guy next to you has been there for 20 years, don't be afraid to speak up. Okay? How many people in here smoke? Oh, come on, Jose. Get there, come on. Okay, yeah, see? You know, yeah, I smoke, yeah. What do you do? You know, that's where they started. I take in this stuff all the time anyway, so I figure it's not gonna hurt me when I walk into a house. It doesn't take long. Okay? Because I don't know what's burning in there. You know? Back in the day when we were dealing with actual 2x4s and that were burning and real wood that was burning, we had complete combustion. So we could go in and what was burning? Organic materials. They were completely burning. What gas did we have being given off? Carbon dioxide. We didn't have a problem. Now we're dealing with fake wood, glues, you know, rubbers, plastics, and everything else. Are we getting complete combustion out of everything? No. So now we're getting our carbon monoxide. Now we're getting our hydrogen cyanide. Yeah, we want to be the big, bad, tough guys, and I'm going to stay in here as long as I can, and I don't need to wear an SCBA because it's fine in here, and I'm not having any problems breathing, but don't be big and bad. Don't be afraid to put on and leave that SCBA on. If your department doesn't have it, have standards set into place that you can only have so many bottles before you go to rehab, so that you can make sure that all your vital signs are in line and that you get enough time to take a break. You know, as we talked into the health side of it, take that break, let your body recover, make sure everything's okay before you go back and stress it out too much. So products of combustion generate, if fuel burns, chemical changes, so flame. Flame's visible. It's luminous, it's body of burning gas. Flame gives off two things. What does it usually give off? Heat and
Smoke.
light. Okay? Flame will give you heat. We know that. It gives you light. Okay? So in the second objective, the impact of thermal energy on heat, temperature, and the transfer of heat or heat transfer. So thermal energy or heat is the energy of an element in both fire models. Both in non-flammable and flammable models, they both give off the same thing, which is heat. Okay? Heat's the kinetic energy. Simple physics. Heat goes from hot and cold. Which way does the balance go? Transfers from hot to cold, right? That's why when we put a pot of boiling water or a pot of water on the stove, we put it on top and the flame doesn't go out, the water boils, right? Because hot goes to cold. Simple physics, we all learned it back in probably high school at some point in time, just didn't know it at the time. Okay? It's always in transit. What's that mean? It's always moving, okay? Because if I'm 75 degrees, or my body temperature is 98.6 degrees, and this table is 80 degrees, which way is the heat going? It's always going to the table, right? Okay, till when? Till it equals out, okay? At that point in time, the transfer stops. What if somebody puts a little heat underneath the table and heats the table up? Which way does the heat go then? Gets it up to 100 degrees. Now it comes back to me, starts to heat my hand up. Okay, hot goes to cold all the time. So thermokinetic, it needs its release. It's got to take that. It's got that potential energy that wants to become kinetic energy, right? What's it mean by it vibrates molecules? So chemical reaction starts to take place. The molecules start to heat up. They start doing what? They start vibrating, and then they do what? They break down, and what do we have? The gas, right? Those break down, we get the gas, that's the vapors. The vapors, that's the release, that's what's going to cause the fire. Heat and temperature. This just goes through just a quick lesson, just a quick chemistry lesson. The importance of knowing how to convert from Celsius to Fahrenheit. If you know it, great. If you don't, it's not a huge math, it's not a huge thing. Obviously, if you're going to convert from Celsius to Fahrenheit, you take the degree in Celsius, take it times 1.8, and add 32 degrees to it. So the temperature outside was 20 degrees Celsius. 20 degrees times 1.8 is, quick math, 36. 36 plus 32 is?
68. 68.
Yep. Perfect temperature. Yep. Is it something vitally important? Is it something that, some math test you're going to have later? I doubt it. I don't foresee it, but yeah. 1.8 plus 32 gets you from Celsius to Fahrenheit. If you're going to go the other way, subtract the 32 and then divide by the 1.8. So their importance into why they put that in there, I'm not really sure. So just something that they figured you needed to know. What do we need to know about temperature? What is temperature? Measurement of heat. More specifically, it's the measurement of the average kinetic energy of heat, but temperature is the measurement of heat. Sources of thermal energy that we need to know about. So chemical energy is the most common source of heat in combustion reactions. So when any combustible fuel is in contact with oxygen, the potential for oxidation exists, correct? Oxygen's there, material's there, potential's there. Almost always is going for chemical energy when the wow, I need to sleep more today. When the oxidization process exists, the potential gives off thermal energy. So, what is self-heating? Self-heating is a form of oxidization. What's it mean? It doesn't need what? It doesn't need an external heat source. Okay? So if it doesn't need the external heat source, it's able to create heat on its own. What could that create?
Combustion if it was fire.
What kind of combustion? Spontaneous combustion. We talked about it a little earlier when we were talking about the matchstick with the flame to the paper, but then we had the rag in the corner that had a little bit of smoke out. What was happening at that point in time? Spontaneous combustion. So with spontaneous combustion, what factors do we have to have available? What has to be there for spontaneous combustion to happen?
Right, oxygen.
Right amount of oxygen,
Fuel source.
fuel source, some type of what, usually? It's usually an oil of some sorts. The one example they gave in here was a rag soaked in linseed oil. Soaked in linseed oil, balled up, thrown in the corner, okay? The heat itself, so if you just took that same linseed rag and you just laid it out and laid it on the table, would you have spontaneous combustion? Why not?
It's not close enough and not concentrated enough.
The heat that's being produced from the chemical reaction is able to dissipate. It's able to get out, okay? So it's not holding it in. So if it's able to dissipate, it's giving that heat off. If it's not able to dissipate, then it's contained and it's starting to get a little hotter, a little hotter. As it gets hotter, the hotter it gets, the faster the heat builds up. Okay, it gets great enough that temperature gets to that auto ignition temperature. And then there's what? There's enough air in the room to help that chemical process kick off. Right? So, electrical. What's resistance heating?
Light bulb, heating element.
It runs through a source. The resistance in that source is enough that it acts as a conductor, and as that conductor, it creates heat. So an incandescent light bulb, that filament is the what? That's the conductor. Normal incandescent light bulb, go ahead and grab it as it's lit, it's going to be what? Hot. Is it hot enough to create a fire on its own? Not sitting there.
It's touching something
Put-
or close enough.
Close enough to touch something, it can get hot enough, yes. So what about overcurrent or overload? Where do we see that at?
Overcurrent's like a direct short.
Yep.
Overloads, you're working something too hard.
Usually we'll see that at what? Where do we see that at?
Chili feeds.
Yeah. Keep blowing circuits and everything else, we're overloading the
You had
circuit.
something to do with that.
Space heaters.
Space heaters. Where else, resistance heating, let's go back to resistance heating real quick. Other than light bulbs, where in the fire service do we find a lot of our home fires? Why does resistance heating affect?
Dryers.
Dryers,
Space heaters.
space heaters, what was that?
Ovens.
ovens,
Run too much current through extension cord.
through an extension cord. And then what do they do with that damn extension cord?
Tape it up and.
They tape it up, they run it under a what?
Outdoor.
Under a couch, under a door, under a rug. Okay, so we've got an extension cord that's not rated for the amount of current that's going through it. We've now insulated it by putting it underneath a carpet or a rug, so the heat can't be dissipated. And oh, by the way, we walk on that rug all the time, so we're constantly stepping on it, which is gonna break down the sheath of the extension cord, which is going to expose the conductors, the wires, and then it gets hot enough and everything's right there. Okay?
I got a funny story about that. The Walmart in Singing Hills in Sioux City,
Yeah.
when they first built that, I got help with the electrical on it. We had to go back and add circuits for their Christmas display, cause they ran cords down to the displays, and they coiled them up underneath the Christmas trees,
Mhm.
and then they put stuffed animals over top of them. 2 days later, the fire department was there.
Yep. So, not only extension cords, but what else? What other electrical item do we think of that gets overloaded?
Surge protectors.
Surge protectors.
Oh, just keep on tripping.
It is.
I woke up one night. I don't even think I woke up, I think I was still up. And I'm walking through my house and I'm like, something smells hot. I couldn't figure it out. And it was potent, it was pungent. And, you know, my house is kind of an open concept house for an older house. The kitchen's kind of off on it's got its walls, but the rest of the house, the dining room, living room, fireplace room it's all one big area. And I could smell it throughout the entire main level. So I looked around, I couldn't figure it out. So I went to the fire department. I was on Milford, so I ran to the fire department, and I grabbed the tick, and I grabbed the laser. I walked around with my main level, and I'm walking around with the tick. I didn't find anything out of sorts, everything looked the same, nothing was showing me any difference in intensity and temperature on the tick. So I'm like, oh, well, I just couldn't find it, blew it off, no big deal. A couple months later, I was gonna tear up the carpet in my fireplace room and through my living room. And I went over to my computer and I started unplugging everything from my computer and I moved it over to the hardwood and I picked up my surge protector and I'm like, that's weird. And I turned it over and there was a burn mark, a hole in the bottom of my surge protector, and the carpet underneath of it had been burned. Yep. And all I had plugged into it was my computer. My computer, printer, and the speakers was all that was plugged into it. It just had failed to a point, it didn't trip it, it just decided it was time for it to burn. So, it can happen to any of us. So,
I wouldn't
Archie-
say that was an overload, I'd say that was more of a connection.
Yeah, it was just a fail to try to burn my own house down. So, arcing in the electrical, what are we talking about there?
Static.
Static, that's the best way to describe it. Buildup of energy, you gotta be close enough for it to be able to jump, okay? Electrical motors, you see some of it in that range, but the most distinguished example, loose connections, yeah. Actually, I see it quite a bit when we plug the trucks in up at the hospital. We're gonna plug that plug into the power supply, and you'll see it, just as you go to plug it in, you'll see that spark real quick jump across. And then sparking. Basically, that's when you have something arc, the spark, that's when you get that one from, so. Mechanical. What do we talk, what do we get how do we get mechanical energy? What's it caused by usually? Generation, friction. Hands are cold, what do we do? Build up enough friction creates heat. Where's that a problem at usually, like in industries and stuff like that, if stuff isn't lubricated properly enough or cooled enough? Where do we see probably not something you guys really would think of, but, go into like car extrications. If you're not running a set of jaws, you're old school, how many people could do an extrication without a set of jaws? You could. All you need is what?
Salsa.
Sawzall. What else do you need to use with Sawzall?
Blade.
Well,
Oil.
soapy water. Yeah.
And a freeze.
Yeah, something to cool the blade, keep it cool. Basically a spray bottle next to the Sawzall blade. As you're cutting through the metal, just sit there and keep spraying that blade to keep it cool. Because otherwise you've got mechanical energy, you've got friction, the friction creates heat. Is it gonna be a problem in in that scenario of maybe cutting a car? Yeah, you got a fuel leak, create a spark, you've got enough heat generated, you're cutting through the roof and you're cutting through the inside liner, create enough heat, you know, especially if you bind up or something like that, so. So understanding the concept of heat transfer can help in several ways. Okay? So, understand the transfer from initial fuel package to others. So we have a burning object, right? Whether it's a piece of wood or whatever. It's going to transfer its heat to everything around it using what? Convection or exothermic, because exothermic is the heat given off, but convection is what we're going to get with this. Okay? So as it heats the rest of that, heats something next to it, it's then bringing up its heat because hot goes to cold. Okay, so if this table's on fire, it's going to start heating up that table and the air above it. Okay? Would it start that table first or that table? Which one? That one. It's closer. Okay? It's got the idea of the ability for heat transfer because it's closer. Okay? By the time it starts to get over that far, it starts to lose some of its energy that's already been given off. So, transfer of thermal energy is described as what? What's the definition? Heat flux. Okay? Heat flux is the energy transfer over time per unit of surface area. Basically meaning if this table's on fire and I had this big table next to it and on this other side I had a smaller table, okay? Over time, the heat transfer over time, which one would go first? They're the same distance apart, but because of their mass, the smaller one would go first. Okay? And the three mechanisms we use for heat transfer are what? One of them was convection, conduction, and radiation. Okay? So when we're talking about heat transfer for us, we need to estimate, we're going to estimate the size of the fire before we attack it, right? How do we do that in the fire service? Show up, pull up to the house, confirm structure fire, we pull up to the house, the officer on scene gets out, what's the first thing his job should be? To do a
360.
walk around 360. What's he looking for? He wants to know a lot of different things. He wants to know possible location, right? Possible hazards, maybe get an idea of the layout of the house, okay? We can tell layout of the house, and that's that art of reading smoke class that I would encourage you to take at some point in time. Based on the windows in the house, you can almost tell how the house is laid out, right? Okay? So get an idea, understand what other outside structures are available that could be a hindrance to not only putting the fire out, but possibly be another structure we need to worry about. So as we're doing that 360, now we're going to get an idea of the size of the fire, you know, Do we got a little bit of smoke rolling out a window? Do we got a lot of smoke rolling out a window? Do we have a lot of flame coming out? It gives us an idea of how we want to attack the fire itself. If we just think we can go in with a little itty bitty water can and put it out, or if we're gonna need something bigger. And obviously, like we've said multiple times, transfer occurs from warmer to cooler, and the same temperature cannot transfer. So convection. What's convection?
Transfer heat
Through air or liquid. Okay. Divers. Okay. Something you guys deal with, right? We deal with it how? So we're doing an ice rescue. The person's in the water. Okay. Is he gonna get colder in the water faster? Or is he gonna wet? Let's do it this way. Person's on land and he's dry. It's 32 degrees outside. How long till he starts to feel the effects?
Molecules are
Of the
closer
cold.
in the water, so you
Right.
can get.
But what I'm going with is I'm standing on shore,
Right.
dry as a lamb. It's 32 degrees outside and I'm wearing this. How long till I get to that point of hypothermia? Quite a while. Dip me in the water, pull me back out, and do the same thing. Am I gonna get there faster or slower? Faster because of convection, because of the liquid, right? So when we're talking it in the fire service, convection occurs because heat rises, correct? And then the transfer. So when we open up the source, the cool air's at the bottom, the hot air's up top, So we get convection heating because of the air up top is heating extra sources. There's nothing over here that's causing it to be hot other than the heat itself through convection is going to heat it up. And then radiation. Radiation occurs because, I can't say occurs because, what is radiation? Radiation heating. It's using electromagnetic waves with no medium in the middle. So in that case, exothermic heat is given off, and it's preheating everything around it, right? Okay, fire's in the room, I can feel the heat because of radiation. If we put a fan on that heat and we started blowing air towards me, now I'm getting radiant heat and convection heat. Okay, if we put a door in between the two of us and I walked up and I touched the door, what kind of heat is that? Conduction. Okay, so when we're talking radiant heat, one fear we have or one concern we have in the fire service is when we have, especially in the lakes area, when we have a structure fire on a lakeside house. Where does radiant heat become a problem that we don't necessarily think of right away, but it's in the back of our minds or in some of our minds? Because our houses are so close together, okay, can we have an issue with house A on fire and then all of a sudden house B on fire because of radiant heat, especially through windows? Okay, it's not uncommon that if you got a hot enough fire burning in house A and A and B are close enough together that you may see radiant heat ignite the curtains in B. No, she's got to be burning hot, and it's probably going to be, an exterior fire at some point in time, but it gets enough heat through the window pane, causes enough heat to the curtains, and then you get another structure fire. Another structure on fire. Common, not so much. I mean, it'd have to be burning for a while to get it to go, but why don't we take a break? You guys have been sitting. So, fuel. What is fuel? Fuel is any material or substance that is oxidized or burned in a combustion process, also known as the reducing agent, when we're talking about the tetrahedron. Okay? So, excuse me. Fuels are going to be two different forms. They're going to be inorganic or they're going to be organic. So let's talk about inorganic fuels. Inorganic fuels, give me some examples of inorganic.
Alcohol.
Alcohol? Alcohol would be organic. It's a fuel. Or a carbon-based fuel.
Plastic.
Carbon-based. Plastics made out of oils.
Hydrogen or magnesium?
Hydrogen or magnesium. Okay. Inorganic materials do not contain carbon. Okay? That's what an inorganic is. So, magnesium, believe it or not, is more prevalent than you think. It's actually located, and you'll see it in vehicles. Transmissions. Yeah. Dashes. Chevy put magnesium in their dashes for a period of time. I don't know if they still do or not.
Like 70s.
No, it was newer than that.
And Ford put it in there like C4 transmissions.
Yep. So, has anybody ever seen a magnesium fire?
Pretty cool.
Has anybody ever seen what happens when you put fire or water on a magnesium burn? It is violent. It is. So, I've seen it once. I had to change my shorts after it. We had a pickup on fire at a farmstead. We went out and we were hitting it with water, and we got the door propped open. It was still burning pretty heavy underneath the dash, and we hit it with water. magnesium, and it almost explodes. It's just such a violent reaction because it just the cooling process is so violent that it literally was just sparks everywhere. You know, basically liquid magnesium just flying all over the place. So it is violent.
By the bird,
What's that?
by the bird.
Yeah, pretty much. That's all you can really do to it.
I know to burn a big pile of wood up in a hurry.
Yes, it will.
I had a cousin that worked at a gas for a natural gas company and had some of the, so in the ground, they wrap these, they call them like a chode. It's a big magnesium bar
Yeah.
on a wire, and they wrap them around the lines
Okay.
to keep the static, the electricity out of the, you know, as the fuel moves.
Oh, yeah. Yeah, to ground it.
To keep
basically.
it grounded.
Yeah, grounded.
And he had, I don't know, he must have had a couple brand new ones or something. He took them or what, but he just tossed a hole in a big campfire one night. We were drinking beer, and pretty soon all of a sudden, boom, you couldn't even look into it.
Yeah, it's bright, it's hot, and yeah, it is dangerous. That is the definite part of that one is because of the heat and the inability to basically put them out. So, organic fuels. What are we talking about there? Obviously, I've already said it. It contains carbon. So basically, plastics, alcohol, because its fuel is carbon based, gas, wood. Wood is cellulose based. Wood and paper, they're cellulose based, so they're still considered organic. You know, they don't necessarily they have carbon in them, but they're more cellulose based than anything else. So chemical contents of fuel are influenced both by the heat of combustion and the HHR, the heat release rate, the amount of heat that comes off of the item when it's burning, or the thermal energy released. In other words, different materials are going to release more or less heat than others depending on their chemical makeup. That's going to be your heat release rate. That's how that's going to be defined. So, you know, obviously your heat of combustion is the total amount of thermal energy released. What specific amount of the fuel is oxidized. That would be also, you know, you'd be able to feel that in your exothermic reactions. You know, based on whatever it was, the chemical makeup of it, the specific amount of it that there was, is going to give you more heat. The picture that they show on the top of page 223 gives an example of that. If you have one match burning, it's going to get off some heat, and if you add a second match to it, it's going to give you off more heat. In that case, it's going to be 4 times the amount of heat would be released because there's more to burn. And in your heat release rates, you're looking at things like your coffee maker in watts. There's a small little fire. Your trash can's a little bit bigger because of the materials that are involved. Or then your sofas or your couches, obviously, are going to have a lot more of a heat release rate because there's more there. The chemical makeup of it, what's involved in it, there's more there to burn, and the chemical process is going to cause it to burn hotter. So let's talk about gases and how they affect us in the fire service. So when we're talking about gases, we talk about things like vapor density. So vapor density, the midline or the level is 1. The air we breathe, the vapor density is 1. Okay? The examples I give in this, methane has a vapor density that's less than 1, so it causes it to rise. Okay? Chlorine has a vapor density greater than 1, so it causes it to drop. Okay? Let's think of it in other terms. Let's go into the world of natural gas and propane. Okay? Natural gas has a vapor density greater than or less than. So it does what? It says low. Okay? So where does that come into play when we deal in the fire service?
You say less than?
It's its vapor density is greater than air, so it causes it to drop.
I thought you said less than earlier.
I'm tired of it a little bit. That's my excuse, I'm gonna run with it. So, if natural gas has a greater vapor density than air and it causes it to sink, why is that a concern for us? Because if we have a gas leak,
And we're on the ground.
where's it gonna settle? Low-lying areas, okay? Has anybody ever seen the videos of house explosions? Okay, major propane, a major gas leak in a community. It goes to low-lying areas, path of least resistance, gets down to the basement, and what happens?
House off the foundation.
Something causes it to ignite, violent explosion, and it goes boom. Okay? So in the same regards as vapor density, if we go into the world of So we talked about this a little bit about the solubility. Solubility is the extent to which a substance will mix with water. Okay. Miscible is it'll mix in any proportion. We said it already. Hydrocarbons don't mix. However, polar solvents, they readily will mix. Your methanols, your ethanols, stuff like that. So density is also a factor when we consider regarding liquid fuels. Liquids that are less dense than water are difficult to extinguish with water alone because they don't mix well with water, and by adding water, all we're necessarily doing is just dispersing the liquid, causing the area to be spread out. So we need to use a different agent or the more appropriate agent when we're talking about trying to extinguish those. So a water-soluble mix with an agent becomes less effective. So we got to avoid using foam specifically designed for polar solvents. So that's why when you get into talking about Class A and Class B foams, why Class A foams aren't designed to be put on Class B fires and vice versa, because of their uses and how they go about extinguishing a fire. So let's talk a little bit about the properties that a solid fuel uses to influence pyrolysis. What is pyrolysis or pyrolysis?
Change solid to gas.
Solid to a gas. Or solid to a gas. That's pyrolysis. Okay. So based on that, as we look at the scenario, or the slider part on the left side of this one, it shows you that the energy required for ignition and the service to mass ratio. So the higher the service to mass ratio, the lower the energy required for ignition. We kind of all understand that, right? We built campfires, so we don't start with the biggest log in the world to try and start a campfire. We always start with twigs or kindling because their service to mass ratio is to the point that it's easier to light, gives off a little bit enough heat to be lit, which in turn will help us walk up the chain. Where in this part they're using sanding dust, sawdust, all the way up through boards and then logs in general. Something else we have to deal with when we're talking about the influence of it is the materials and how they're situated. Kind of common practice. We all know that if we were to light a board on fire and it was standing upright, if we light it in the bottom corner, its point of ignition, and as it builds up, the fire is going to spread faster because heat rises. So it's preheating as it walks up. Okay, so this is already warm enough that it works its way up. Where if we're doing it where that same board is lying flat, it takes more energy and takes longer for it to preheat out the edges using exothermic energy than it would if the board was standing straight up and down. What's important about this part of it when we're dealing in house fires? When we're talking about preheating things. Fire starts in the corner. Okay? Is it going to go up or is it going to go out? It's going to go up. Okay? And we'll get into it later, but it gets to a certain point that when it gets up where it can't completely burn, it's still, so in this scenario, in this room that we're in now, if we were to start a fire in the corner, it's going to work its way up and out. Well, at a certain point, it's going to take care of the ceiling, and then what is it going to try and do? And try and continue to go up. So if we have a second story, now we have to worry about the flooring on the second story becoming an issue as well. Safety. The air we breathe is naturally 21% oxygen enriched. Okay? Everybody pretty much already knows that. At normal temperatures, materials can ignite and burn at concentrations as low as 14%. Okay? The oxygen we breathe in, we already said, is 21%. Out of that 21% that we breathe in, your body doesn't use it all. We talked about that when we were discussing CPR. That's why mouth to mouth or mouth to mask CPR works, because as we exhale, we're exhaling the oxygen we didn't use. That concentration is right around the 14% mark. So that's why when we blow on a fire, we blow on it at the proper rate, it'll actually help fan the fire, build it, because we're still giving it the oxygen it needs. Obviously, limited oxygen diminishes the flaming combustion. Why is that? If there's less oxygen, it affects the what?
Combustion ratio.
The combustion ratio. It takes care of the chemical reaction. Okay? Oxygen is considered an oxidizer. It reacts with the fuels in much the same way as others do. Other oxidizers could be chlorine gas, hydrogen peroxide in its liquid form, methyl ethyl ketone peroxide, stuff like that. Non-flaming combustions can operate in a lower oxygen concentrations, even when the surrounding environment's relatively low temperatures. However, at ambient temperatures, flaming combustions may continue at considerably lower oxygen concentration. So once it's started, it may have enough oxygen, and you may be able to pull some of that oxygen out, but the flaming combustion will still continue once it's already started. Materials that will burn in a readily oxygenated environment will burn even faster and greater with more heat when the environment is more enriched with the oxygen. Okay, it helps that chemical process out. In that same sense, though, materials that normally don't burn in a normal oxygen enriched will burn more readily in a oxygen-rich atmosphere. Does anybody know of one? We wear it.
Nomex.
Nomex. At normal oxygen, your Nomex will not burn. You get into an oxygen-enriched environment, Nomex will burn more readily. Nomex, it's a fire-resistant fabric. It's used in construction of many types of protective clothing, obviously worn by us. About 31% is the number needed for Nomex to start to burn. So that's why it works well for us, because we don't get into oxygen-enriched environments. And those areas that do have that type of atmosphere is already known. You know, you're looking at chemical areas, maybe somebody like down in Sioux City, they've got, well, we've got it up here that has got the gas. Air gas, where they've got liquid gas and stuff like that.
At ammonia plants, they have, can't think of the word now, where they make oxygen, pure oxygen.
Okay. So you're gonna have a higher enriched area in that as well, so. Ambient temperatures are gonna impact it. We already talked about that, about the non-flaming and flaming. Obviously, non-flaming can burn in a sense at a lower oxygen level, and higher oxygen concentrations will help a combustible fire, a flammable fire burn hotter and greater when the concentration is up. So there's two terms in there that we need to know about. Obviously, we know about the flammable range. So the lower end of the flammable range, what do we call that? There's a term for it. It's on your, and it'll be on your meters. If anybody's operated a gas meter,
The LEL.
the LEL, the lower explosive limit. Okay, that's about your 45%, depending on the gas. And then what's the top number? Upper. The upper explosive limit or upper flammable limit So the lower, anything below the lower explosive limit is too lean. Anything above the upper flammable limit is you're too rich. Alright? Understand your LELs and your UELs. So I'm surprised they don't talk about it more in the. So back to the combustion of methane and oxygen. Methane and oxygen are provided, they're a good example because complete oxidization of methane results in the production of carbon dioxide and water. It also gives off heat and light. It also gives off CO, formaldehyde, and free radicals. So free radicals are what? Just little molecules that just kind of do their own little thing. Okay? So then those free radicals are going to combine with oxygen or the elements of the form of the fuel material itself. In this case, it's methane, carbon, and hydrogen. And they're going to produce an intermediate combustion product or a new substance. They produce even more free radicals, which then in turn are going to combine with everything else. Ultimately, what it does is it increases the oxidation process, increases the reaction. Basically, it's gonna burn until the fuel, the oxygen's exhausted. You know, it's just gonna keep producing itself until either the oxygen's out or the fuel's out. So, remember that carbon monoxide is flammable. Also understand that formaldehyde is flammable. So obviously if it's creating that as it's burning, it's just giving itself creating its own fuel throughout the entire process. Basically those free radicals that it's producing, you know, through the combustion process, most of which it's going to create as it's burning, it's going to create its own fuel. They're going to be toxic, flammable. You get enough sufficient heat available, it's going to cause the fuel and the oxygen to form more free radicals. That's what's going to initiate the self-sustained chemical reaction. It's going to be able to do it on its own. So what's a chemical flame inhibition? That's something that occurs with an extinguishing agent. Dry chemicals, halon-like agents, they're going to interfere with that chemical reaction. Basically what they do is they just form a stable product so that we don't continue the self-sustained chemical reaction. Halon, well, have you guys seen those fire extinguishers they show like on combine fires? The guy jumps out, he's got this little itty bitty fire extinguisher and he just pushes the button and you don't see anything come out, then all of a sudden the fire's out. You just see it just kind of, fire just die out. That's a halon-like substance. There was commercials on it for a while. You'll see them at fire schools at times, and they'll have videos of them.
So over the old glass bulbs with the liquid in.
Yeah, that was a halon style. Halon itself, last I knew, was not acceptable. It was not to be used. They now have halon-like. So factors that are going to affect fire development. We're also going to talk about the stages of fire throughout this next objectives. So fuel types. The fuel types themselves are going to affect the heat release. So depending on the fuel, the fuel involved in the combustion, it's going to affect the HRR, or the heat release rate. And any fire that's involved in a B and a C are eventually going to turn into an A, fuel fire. Okay? So Class A fires are what? And you'll learn this more later, but we'll get into it a little bit now. Class A fires are what?
Wood, paper.
Wood, paper, okay? Class B fires are, so Class A, going back to a little bit earlier, are cellular-based materials, woods, papers, okay? Class B fires are
Liquids.
carbon-based, okay? Gasolines, oil, stuff like that. Class C fires are electrically charged fires. Okay? That's the key. When you talk about a Class C fire, the key part of it is electrically charged. Okay? Fires involve a single type are rare. Usually you're going to have multiple different types, even in this room, because you've got different materials. You get compartment fires because of gas leaks, stuff like that. So your availability and location of additional fuel based on your building configuration, the construction materials used, what's in it, the proximity of initial fire to the exposed fuel sources. All of those are going to have are different factors that are going to affect the fire development itself. So we take a room the size that we have right now, and I'm not even going to terrible at measurements, so I'm not even going to try and guess. Let's say 15 by 30, we'll say. And we take everything in here, and we were to start a fire in here. The fire is going to progress at a semi-decent rate. But if we were to take all the same materials that we have in this room right now, and we were to put them in a 5 by 10 room. Same fuel load, but we change the compartment size. Is it going to change what the fire is going to do? Yes, immensely. So, houses ventilate themselves. Obviously, we discussed that a little bit. We, in turn, also have the availability to ventilate a house in different manners. The example I can have for you is on a knowledge-based. We got called to a house in Wabaton on a dead-end street, and when we pulled up, we had smoke just rolling to us. And we pulled up and we got to a point that we thought we were at the house. And we got out, crews got out, chief went to do his 360, and the house we were sitting in front of was not on fire. 2 houses down, the house was on fire. So the fire had started in the roof on the lake side. Wind was blowing off the lake into the house. It was feeding itself. It had gotten so hot and burned so long that it smoked it up enough that it was basically pushing the smoke down the street. And it was smoked up enough that we literally had no idea that was the house. So we made entry, we got to the front door. My first partner and I got to the front door, had hose line in hands, went to open the front door, and my partner's regulator failed. It's kind of common for him. And so I waited. Second partner comes in. We make entry into the house, walk into the living room, and it's clear as can be. I walked in the house, no fire present at all. It's smoking to be hell outside. We walked in, nothing. Mind you, we left the front door open. So we walk into the living room, and in the corner, there is a baby grand piano. So, the process works its way through, and you've got, what's the first thing we're worried about? In any fire situation, in any emergency situation, who do we worry about first?
People.
Which people? Me. I'm going home. Okay, I got a daughter to go home to. I'm going home. Okay. Then we worry about life safety, property conservation down the line, right? So I know I'm safe because I can walk in, I don't see anything. The guy that was in the house, cops were able to drag his rear end out because he did not want to leave. He was not leaving his house. They ended up having to drag him out. So we walk in and there's this beautiful baby grand piano in the corner. And I want to look in the ceiling above that baby grand. Mind you, the front door is still open. Okay, so me and my partner, we moved the baby grand piano out of the way. And I take a Clemens hook and I punch it up in the ceiling. And he's holding an 1.5 hose. I punch a hole up in the ceiling, run it around a little bit, pull it down, and I look up, and it is a glow, a bright glow. Well, I'm behind it. Okay, if I'm glowing that hard now, I know I'm behind it. The fire's further back this way. So we walk back about 3 feet, and I punch another hole. And by this time, another crew's coming in with an 1.5 inch, and I punch this hole. Mind you, the front door's still open. Punch another hole, and it's still glowing. I backed up another 3 feet, punched another hole, still glowing. Finally, I just made the hole big enough. The second crew that come in had gone back out and grabbed a 2.5, come back in, stuck a 2.5 up. Oh, by the way, the front door's still open. And just started deluging the roof. And we're working it, we're working, we're in there 3-4 minutes. Front door's still open. And I mean open, wide open. And pretty soon I hear the air horns go off. And I'm the officer in charge inside of a 4-man crew. And I looked at all my crew members and said, get your asses out, let's go. They start walking, pulling hoses as they go. Officer inside, I'm the last one out the door. As I'm walking out the door, that has been wide open the entire time, the fire's coming down on top of us. We helped ventilate that fire because we left the front door open. Because it was blowing in from the lake, took all that heat and that smoke, and did what? Gave it an exit. It never went through the roof, it gave it an exit, and it worked its way out and found an outlet, so it worked its way back to that front door. The reason they hit the air horns or they get your rear ends out was because they had seen it come out above the front door and knew that the entire ceiling, the entire roof line was on fire. So in the ventilation idea of this whole thing, we can affect it. If you're working a house fire, and if you guys haven't discussed A, B, C, and D's yet, right? Okay, so if I say the A side of a structure, A side of the structure is the street side. The side that you pull up on is the A side of a building. And then it's clockwise, A, B, C, and D. Okay? We need to be aware of windward, leeward sides. When we're dealing with structure fires, when we want to ventilate. We always want to have ventilation in place and ready to be a use to us, but understand its limitations. So we never want to open up which side of a windward, leeward when we're dealing with structure fire. Which side should we open first? What's the more important side to open? If we want to use ventilation as an asset. And why would we use ventilation? What do we want to get out? Smoke and heat. Okay? So what side, downwind or upwind, what side do we want to open up first? Downwind. Open up the downwind side first, because if you open up the upwind side first, you're feeding what to the fire? Air to the fire. Okay, so now you're giving it everything it needs, and it's got nowhere for it to go. So it stays in the compartment. Okay? That's where ventilation fans and everything else, when you're using those, you need to understand what you're using and what their capabilities are. Okay? A normal ventilation fan placed at the front door will not overpower a 10-mile-per-hour wind. So if you open up a ventilation fan, you start a ventilation fan, and you go to the other side of the house, which is the upwind side, and you open up the window, that ventilation fan will not overpower that 10-mile-per-hour wind to come through that door. It will not change the pressures enough, and it will cause the fire to work back at you. Okay, so be very aware of how you use your ventilation, its limitations, but use it to your advantage, because yes, you can use it to help clear the heat out, clear the smoke out, so that it can make your visibility better. It can make life safety more readily available because you're getting the heat out of there as well. Ambient temperatures are going to have a factor on fire behavior as well. High humidity, cooler temperatures. Strong winds, we just discussed that. If a window fails, we've kind of discussed that. Wind direction, velocity. You know, the stronger the wind, the more it can be a hindrance to you, but the more it can help you as well. The higher the humidity, the cooler the temperatures, it's going to do what to the fire? It's going to cause it to grow slower. Okay? Atmospheric pressure is going to be involved in it as well. It actually causes the smoke to stay closer to the ground. The air is thicker. It won't allow it to grow. There was one in here too, and I don't remember it. One of them, I gotta find it. Colder temperatures. Colder temperatures will actually affect the color of smoke. So be aware of that. So in temperatures like we have today, will actually give that smoke a wider effect than it would if it was 75 degrees outside. So be aware of your ambient temperatures as well, affecting what you perceive is going on. You know, you pull up to a scene and you look like you got some nice white smoke coming out and you think everything's going to be okay, but understand that because of the cooler temperatures that it's going to affect what you see rather than what's actually going on. Fuel load. Fuel load is what?
How much fuel you have?
The quantity. What's in there? How much of it's in there? Fuel load, we also call it the fire load. Anywhere from the furnishings, the merchandise, what the interior finish is, whether it's carpet or hardwood floors. The structural components can be something we need to work to look into. Go back to the old home, new homes idea. Old homes, when they built the roofs and they built the structural frames of each floor, what did they use? 2x8s, 2x10s. Now what are they using?
2x6.
Pressed wood.
Pressed wood, yeah.
Yeah. Yeah, they work great. The house isn't as heavy. You know, it's not as, you know, the roof load isn't as heavy because they're not using such heavy materials. It keeps the cost down of the house. It burns faster. It burns hotter, which means it's going to fail faster. Okay? So my house that was built in 1920 is going to last a lot longer because it actually has true 2x4 studs than a house that got built a year ago that's got the pressed wood rafters in it. Okay? Can rafter plates be an issue? Because they get hot, they fail, they pop. Now the rafter can fall apart. So your structural components are going to have issues as well, not only on what the fire will do because of how hot and how fast stuff like that will burn, but also the idea that we need to be aware of those because the idea that they fail faster. So, occupancy types, whether it's a single family home, whether it's a mobile home, whether it's a multi-family apartment complex, stuff like that's going to be a factor. You talk about like assisted living factors, you know, do they have fire breaks in the roof lines? You know, or is it just one big continuous roof? So, you know, there's all, and this is stuff that you can only estimate on scene, you know, unless you are proactive as your department and you're going out and do pre-plans, you can look at some of that stuff, but A lot of it, you learn from experience, you look at it, you can tell what's going on. You may be able to tell by the newness or the oldness of the house, what kind of materials you may be dealing with, whether it's the old style, the new style, which will tell you how fast you think it's gonna burn, how slow you might think it will burn. Stuff like that to help you. So 57. Jose's got the PD. Don't worry. I just told everybody that's not here that you're going to the bathroom. We'll let Jose get back before we get into the stages here. Is anybody else going to use the restroom? No? Okay. All right. Jose's back.
Thank you.
Now you. So we're going to get into the stages of a fire. Fire has 4 stages. Okay. First stage is the incipient stage. It is what it is. It's the beginning stage. It's basically when there's an ignition, when the 3 elements of fire combustion are readily available. The process begins. At this point, the fire is small and it's combined to the material that's first ignited. Okay? During this phase in the fire development, radiant heat is going to warm the adjacent fuel loads. Okay? We talked about radiant heat earlier. It's going to preheat everything around it. Do the process of pyrolysis. Your plume of hot gases are going to start to rise from that fire. It's going to mix with the cooler air in the room, start warming that air up. It's going to get to the ceiling. Those hot gases are going to start to spread horizontally because they're looking for path of least resistance. It wants to go up, but if it can't go up, it goes out. So now the fire started in the corner. It's starting to, through radiant heat, it's starting to heat everything else around it. It's starting to heat the air as it starts to climb. Those hot gases are going to get to the ceiling level in the corner. They can't go up anymore, so they start to work their way out. Originally it was called the mushroom effect, and now referring to it as a ceiling jet. Those hot gases are going to get in contact with other surfaces in the compartment, and they're going to start preheating those as well. Okay? Small fire. We've all seen them at some stage. Easy to put out, not much water is needed. From that point in time, we get into the growth stage. Okay? This is where the fire starts to influence the environment and the compartments. It's grown large enough at this point in time that the compartment configuration, the amount of ventilation, is going to start to influence it as well. The location of the fire when the growth stage occurs has an influence on it as well. So if it starts in the middle of the room, okay, it's gonna get air, fuel from all sides, right? If it starts on the wall, now it's just from 3 sides, and if it starts in the corner, it's only gonna be entrained from 2 sides. We're gonna start getting into what we call thermal layering. Okay, thermal layering is where the gases up at the ceiling level are gonna get hotter, but as you work its way down, it starts to get a little cooler. This is the whole reason that when we walk into a room that's on fire, what do? We get as low as possible. Do we have to crawl? Only when necessary. Don't get to the idea that every time you walk into a room that's on fire that you gotta crawl. Okay? Get to the level that you can be comfortable. If it means you gotta get on your hands and knees, by all means get on your hands and knees. If you can get on a one knee and do the scoot, get on one knee and do the scoot. If you can walk into it, walk into it. Okay? You'll feel the thermal layering, you'll feel it as it comes down. As we go through this, you're gonna start to see how you can see it. Especially after, if you've ever been into a house fire after it's been put out, look at the walls. It'll be really dark up top, and you'll start to see the color changes as it works its way down. Okay? You'll have, what we start to see is isolated flames. Isolated flames are, remember, what is smoke? Smoke is fuel. Okay? So the fire started to grow. We're starting to preheat everything around it. It's climbed up. We're starting to get what we call thermal layering. The top of the thermal chamber is the hottest. It works its way down. It's going to get to a certain point at the top level that it's going to start getting hot enough to want to start to light off. You're going to start to see isolated flames, or you're going to see them start walking. So you'll be able to look up, and you're going to start seeing little flames dancing above your head. Those are isolated flames. Okay? Your heat level at the top is almost to the point of ignition. Okay? Its richness and everything else is still a factor, but you're getting to that point. Okay? At a certain point, if we haven't cooled the atmosphere, and you'll learn this when we start getting into hose handling and streams and nozzle patterns and stuff like that, is when we start seeing the dances, the isolated flames, that's our first key that it's going to get bad quick. Okay? We need to cool that atmosphere. Best way to cool the atmosphere is the tools in hand. Right? All we do, lean back, put a couple sprays up in the wall, get a nice tight pattern, lean back, open, close, open, close, open, close. Okay? When we do that, we're putting water into that upper atmosphere. When that happens, it's going to come down on top of us, right? Water goes up, it's got to come down. If the water comes down in large droplets, it starts raining on us, good thing, bad thing? Good thing. It's not hot enough yet. If we put a couple spurts up in the air, and you get slammed by steam, and I do mean you will get slammed by steam, good thing, bad thing? Because we are almost to that point. Okay? So, you go into a room, we're in the growth stage, you know thermal layering is happening because our visibility is really low. You look up, you start seeing the dances, you put 3 squirts of water in the air, you get slammed by steam, and we don't have any visible sight on the fire yet. Stay or go. Just shoot your hands out. Okay? Because you're almost to that stage. What's that stage going to turn into? rapid growth, fully developed stage is also known as flashover. Flashover is the almost simultaneously auto ignition of everything in the room. You cannot run faster than the fire will grow. That's why we have to pay attention to everything going on. Okay? So here it's talking about the thermal layering of gases. You see in the slide, darker at the top, wider at the bottom. Your neutral plane. Neutral plane is that point in time where you still, it's smoked up top, but you got good visibility underneath where the fire's at. Okay? Because this is all burning, and this is the unburned carbon at the top of it. Your increased smoke volume is going to cause that neutral plane to descend. The more unburned fuel you got, the more smoke that builds up top, the more that neutral plane comes down, which is what affects our visibility. We start to feel the heat, which causes us to get lower. Other rapid transitions. So we've talked about flashover. What's the other two that we need to talk about? Backdraft. Smoke explosion. So let's talk about backdraft a little bit. Backdraft is going to occur when the ventilation is controlled in the house. Those tight houses are they don't breathe well. So you pull up to a structure and you're seeing some smoke come out, but you're not seeing a lot of it. The smoke you are seeing is black. It's yellow. It's puffy. So where it is able to release, it's kind of puffing out those voids. It's not just rolling out the voids. It's kind of puffing. It really is. It's a yellow. It's an icky looking smoke. And that's because of the amount of fuel that's still in the smoke. Okay? What is it waiting for?
Oxygen.
It needs oxygen. So that means when you run up to the front door, whip that front door wide open, right? How about we not? What's the best way to take care of that situation? We got to get inside, but we got to get inside safely. So we got to take care of the atmosphere inside somehow. What's the best way to do that? We got to get all that nasty stuff out, right? Get all that heat out. So we're going to cut a hole
In the roof.
in the roof. Let it go out. It's going to go out faster than it's going to come back in. Okay? Backdraft happens when the ventilation's so controlled it starts to basically suffocate itself, and then all of a sudden it has a sudden rush of oxygen put to it, causing it to basically explode. The movie, if you've ever seen Backdraft, the movie, it does a somewhat reasonable version of it. It's not the best in the world. It's, movie driven, but the idea is there. They just don't show it with the smoke. They basically show it's a decayed fire. They put oxygen to it and it explodes. No, you can usually tell the factors. Actually, in the windows, you'll be able to see the windows almost pulsing as well. It's basically, what it's doing is it's trying to suck in the air it needs. It just can't do it. If you were to leave it go long enough, it would probably put itself out. But at some point in time, you got to open it up to get the smoke out. And if it's just got even a little bit of heat in there that it needs, that would be enough. Obviously, your building indicators are going to be there. The fire's combined to a single compartment or into a void space. Dense smoke, gray. The neutral plane is going to rise the lower the similar. It's pulsating, or it's going to look like it's breathing. It's a high heat, smoke stained windows. will be a factor, but there's going to be little to no visible flame when you start looking in. So you get close to the windows and they're going to be hot as all get out, but you're not going to see much. Smoke explosion, not a very common thing that I'm aware of. Basically, they're violent because they involve a premixed fuel and oxygen. Similar to an ignition of a propane and air when it's in its flammable range. So as it goes through its growth stage, gets into its fully developed stage, at a certain point in time, it's going to run out of fuel and it's going to start to go through the decay stage. At that point in time, it's going to be stopped by two means. Oxygen's probably pretty readable, so it's either going to A, run out of fuel, or it's going to run out of heat. So what are the four stages again? First stage is incipient stage. Second stage is the growth stage. Develops into the fully developed, and ultimately goes to the decay stage. So we're getting close here, guys, so I'm not going to bother taking that break this last hour. So rapid fire development is reasonable for numerous deaths and injuries throughout the fire service. We need to learn to, obviously, like I said to begin with, we're going to protect ourselves, because if I'm watching my 6 and you're watching your 6, then we're protecting ourselves, which means then we're protecting our crew as well. So we need to be able to recognize the indicators that are out there, need to know the conditions that can be created, and take the best action that we can based on what we can see and what we know. And we want to do that before we start rather than in the middle of. So let's talk a little bit more about flashover. Obviously, it typically, once again, and the reason I'm going to discuss it more is just because of the factor that it is in fighting a fire, it is the things that we need to pay attention to the most. Obviously, it typically grows during the growth stage. Like I said, it may and can develop during the fully developed stage. The environment of the room is going to change it from a 2-layer condition to a single well mix. When you're talking about the hot gases that are involved, you're going to transition between the pre-flashover and the post-flashover, and it's going to go quick. Volume of the fire can fill the entire room, and probably will fill the entire room. And it could be violent enough when you open up that door, if the door is open, that it's going to push those hot gases out into other openings, out into your hallway and stuff like that. So now you may have a room that flashed over, and as that picture showed you a little bit ago, if it was a room like this and you open up that door, now it's pushed it out into the door, and now we're into the hallway as well. The factors, we talked about them: ignition of exposed surfaces, transition, the rapidity or how fast it's going to move, and the compartment size itself. Obviously in a room like this, flashover would occur at some point in time, but may not be as violent as you go into the living room of a house that's got couches and chairs and stuff like that. Two factors: the amount of fuel, the HRR, and ventilation, because it's got to have enough oxygen. There's the factors that it talked about. You'll see the rollover, the dancing of the flames, and the building, the smoke, airflow, everything we've already talked about. Picture that they're using for backdraft. If you guys go on YouTube and just pull up backdraft videos, there's been some of them out there. Most recently, one I think was in New York City. And there was a crew of about 6 of them standing outside basically with kind of a department store idea storefront, and it was just sitting there smoking, and pretty soon the smoke diminished a little bit, and then she exploded, and all you see was stuff flying, smoke come pouring out, and so talked about the indicators already. The volume of smoke we talked about, the confinement, the pressure inside, the speed of which everything gets mixed. Here it talks a little bit more about the smoke explosion. The cooling of smoke can accumulate in other areas. So you got that smoke is fuel idea. It gets into little compartment areas. It's its own fuel. It mixes with nice cool air. So it's a pre-mixed. It's got its oxygen. So you put the heat gets to it. That's why it's kind of violent. Be just like you have a gasoline. Well, maybe a natural gas explosion. Same idea. It's just from a fire that's already burned. That smoke generally it's going to get down to less than 1100 degrees. So what can we do to influence the fire behavior? Obviously through temperature reduction. Water's our most common method. We all know that. That's why we drive around in trucks that have water in them, and we have fire hydrants in our towns. Hopefully they always work. Sometimes they do, sometimes they don't. Sometimes you hook up to them and you pull a hose, you pull your line, and the hydrant falls over. Spirit Lake. Oh. Water has its greatest effect is when it's converted into steam. Now, does anybody know the expansion number? Water into steam. Water expands into steam at how many times? A molecule of water will expand how many times before it turns into steam? What was that?
170 is right.
Nah, you got the numbers right, but you're missing a zero. 1,700 times. Okay? That is, I will tell you, every test I've ever seen for firefighter 1, that is a number you will want to know. Water to steam expansion ratio is 1,700 times. Okay? So water is used to control the burning of the gases. It reduces the temperature through an endothermic production. It does its greatest expansion at 1,700, or as a steam. So when we're using a nozzle pattern, and you'll learn this as we get going, is straight streams over fog streams. Straight streams work better because it's more dense. It takes more energy for the fire to turn that water into steam as large molecules than it does if we use a fog pattern and we got finer molecules coming out. It doesn't take as much energy for that fire to turn it into steam. Therefore, it's not able to cool as fast. We can do it through fuel removal. It's the simplest, but allow it to burn until it's all consumed. And sometimes we have to. Hay bale fires. Anybody been on one of them? They suck. If there's nothing around it that's going to be of a problem, let the SOB burn.
There's always something around it.
Yeah. Because what's our option? I mean, you guys been to them?
Throw a lot of water on it. So
You know.
can do.
The other option is you got to
How would they have roll them out?
bring the tractor over and start rolling them out.
Yep.
That sucks. I've done that once. I will never do it again.
Be on Highway 9?
No, mine was, I don't remember where ours was at. Though, yeah. Oh, we were out in the country, out east of town somewhere. It was just a small one. It was like one hay bale that something had happened in the baler and it started on fire. That was one bale. I don't know. We're just sitting here pushing it along. Just kept pushing the damn thing. I'm like, this sucks. I don't ever want to do this again.
There's one of those out by north of Westerville.
Yeah. Superior had that big one.
And then they used to,
That was
we
wrong.
had
That was
about
done
100 bales
wrong.
pushed out from the side
That
of the
was
pile.
like
Yeah. Yeah, because Milford had one that was Durner's. Durner had hay bales that were on fire, and the wind was blowing, so it was blowing it on top of his that big feed pile that he's got. So it's putting embers on top of. We had a crew up on top of that, just putting little embers out on top of his feed pile. So
Yeah, when it's fall, a guy took the bale out, turned around, almost looked bad, and the whole bale was on fire.
yeah, those things suck. Yeah, just let the dang things burn if you can. So oxygen exclusion is another option. Obviously, it's probably the most difficult. And obviously it won't work if that fuel's self-oxidizing. We talked about that earlier, that it basically is just, it's going through its process and creating free radicals, and the free radicals are merging with other things, and it's able to do its own thing. So, close the door if you can, take the air out of it. So that's why when we go through and we start doing search and rescue operations, if you come to a door, open the door, search the room, close the door. Okay? If you're at home, you go home tonight and you crawl into bed, close your bedroom door. Unless you got a cat that paws at the door on a continual basis. No, you can't shoot the cat. Doesn't work that way. Right. Yeah. No.
Let it outside.
Mine are smarter than that. They know where the food supply is at. They're mad at me as it is. Feed me, damn it.
You're missing a cat tonight.
Tonight, if you let it outside, it might not come back. You'll find it in the morning.
So yeah, we don't think about it much, but yeah, you just create compartments throughout your house. So if you do have a fire, yeah, you start getting smoke bleeding into the room, but you're not going to get the heat because you've created a compartment. And as we do search and rescue operations, as we do stuff like that, that's why when I kept telling you about that house fire in Wapaton, when I kept telling you that we left the front door wide open, we were giving it air because we didn't create a compartment. I'm not saying, obviously we can't shut the door because we got hoses running through it, but we can start eliminating as we need to. So. Chemical flame inhibition using agents to interrupt the combustion reactions. It's effective on gas and liquid fuels. So gas and liquid fuels, what classification is that in the fire? A, B, C, D, E, B, Class B fires. Obviously, using this method with the chemical flame inhibition, obviously it's not easily extinguishable. The non-flammables, it's not practical on the smoldering fires. The reason it works well on the gas and liquid fuel fires is it cuts off the gas from getting out. So Class B foams, which is what we use on fuel fires, it doesn't put the fire out in a sense of what we normally think. If you take a container of gas, and we know because of the temperature that it's going to be vaporizing itself, basically that Class B foam puts a blanket on top of it, so the heat and the vaporization can't meet anymore. It can't get through the foam. And we'll learn more about that as we get into that later throughout. Unplanned ventilation can occur before or after suppression operations are going to start. Basically due to the result of wind outside the structure. Increased pressure inside the structure, because greater to smaller, not only does it work with heat, but it works with liquids, it works with air, it works when we're breathing. We're sitting here breathing and all we're doing is just changing the pressure from inside our lungs to outside. Okay? When you inhale, you're basically changing the pressure inside your lungs so air rushes in. When you exhale, you're changing the pressure inside, which forces it back out. Same idea when we're talking in houses. If the pressure outside the house is greater than inside the house, the air outside wants in, and vice versa. And in that case, it's going to drive the smoke, it's going to drive flames into the unburned portions of the house. That also can upset any tactical ventilations, whether we're doing positive pressure ventilation or negative pressure ventilation. We're using positive pressure tactical ventilation, meaning prior to even making entry to the house, that you put a ventilation fan at the front door, and before you even make entry, turn the fan on. You're going to push the fire in that compartment and try to push it outside the house, but you're trying to pressurize the house greater than what the outside air is. Here, I talked about this earlier. Wind-driven conditions can occur any type of structure. Even a 10 mile per hour wind can create wind-driven conditions. Unplanned ventilation is going to occur before or after suppression starts. Could be the result of an occupant, fire effects of the building itself, ventilating through a wall, ventilating through a roof, action outside of the planned ventilation. So, our greatest friends in the world, the boys in blue, they think they're helping, they show up, and they think somebody's inside, and they open doors and break windows. Thanks, guys. But there's also videos out there, and at some point in time, maybe I'll talk to Chris and see if he can't locate them. There's actually a video out there of a house fire that the fire department shows up, and it's just a small one-compartment fire. And one of the old-timers goes through and starts breaking windows, and they lose the house. If they had left it compartmentalized, they'd had a one-room fire, put it out pretty easily. He was trying to get the smoke and everything out, and he just started going through and breaking windows. So there's a department in this town that's done ventilation of windows through extraordinary means. They couldn't reach it with a pike pole, so they started throwing rocks. Ventilation by rock through window. Terrell had a fire where they were doing ventilation and they were breaking out a window with a Halligan and with an axe. They were breaking a window out with an axe, and the axe ended up inside the structure because his hand slipped. So, yeah.
They never got it back either.
Yeah, we did.
Oh, you did?
Yep, they did. So, tactical ventilation is something that you plan. It's systematic. It's not something you're just gonna randomly do. You definitely got to understand and know what you're going to do with it. It's got to be coordinated with your suppression operations. Because if you start it and it goes wrong, it's bad for the crew inside. Because you're basically trying to feed the fire away from them, feed the heat away from them. And if something happens to that ventilation effort, that fire that you've been trying to push away from them can now grow in behind them. It's going to have increased combustion rate, but it's controlled. Your HHR is going to increase, and it can be very simple, or it can be very complex. There was a group of guys coming around from Salt Lake City that were really pushing through this. I went through the class. It was something that they was really looking at going towards, and then it just kind of fell out of. They did more studies on it. It works when done right. So like it said, even coordinated tactical ventilation is going to increase the combustion rate in the ventilation in controlled fires. You're putting air to it, but what you're trying to do is you're trying to push it away from and help with life safety and help with visibility so that you can make entry quick, fast, knock it down. Basically, the theory behind it is if you have a single structure with a fire in a corner, so the idea is if you got a fire in the BC corner in this structure. The idea is, originally you show up and this door is going to be closed. You're going to come in and you're going to place a fan at the A door, at the A side, at the front door. And you're going to have your crew, 2 3-man crew, with their fire hose, ready to make entry. Keep laughing at my pictures.
I am.
At a certain point, you're going to start the fan and you're going to open this front door. However, before this is started, we know that the fire is located here. Your 360's been done, and this window's been eliminated. So you've given it an exit point. Remember, wind, downwind, upwind. Okay? If the wind is blowing that direction, we're not going to do it that way. Wind is in our favor. We open up that front door, wind starts blowing in. It's going to blow that fire and heat where? Out the window. That'll clear the atmosphere. This team can come in and knock it down. Okay? The other option is, prior to this, you have a second team over here. You take the window, spray water in, change the atmosphere, cool the atmosphere, turn the fan on. Now we get the smoke out. Once the fan's on, these guys are not moving water. Okay? Because when you're moving water, what is moving with the water? What else is going with it? Air. Okay? Because we don't necessarily always use a straight stream. We use about a 30-degree stream. It's pushing air in. So we make a knockdown, knock it down a little, fire it up, clear the smoke out. Second crew goes in. Easy, quick knockdown. Tactical ventilation. That's at the simplest level right there. That's the idea behind it. Normally we use ventilation. We'll go in, we'll knock the fire down. We've got the fire basically knocked down. Let's go ahead and start ventilation so we can see better. But we've already basically put the fire out. We're just trying to clear the smoke out. So basically, we just need to understand the combustion process, how fire behaves, and how to select the appropriate extinguishing agents. Okay? Understand fire behavior can help you recognize the developing fire conditions and respond safely to mitigate hazards present in the fire environment.